The origin of mass is one of the greatest mysteries of science. But what exactly is mass? It may seem like a simple question, but knowing the answer will provide us with a much more complete understanding of how the universe works. To get these answers, we must go back to the very beginning, to less than a billionth of a second after the Big Bang. In the first few moments after the Big Bang, the four forces of nature began to split apart, and huge inflationary expansion took place, increasing the size of the universe to unimaginable proportions. In these extremely hot conditions, the fundamental particles began to form and whiz around at the speed of light. Only a small fraction of a second later, some of these particles acquired their mass and allowed the formation of the universe we know of today. This is the standard model of elementary particles that make up the known universe. They are divided into groups called the leptons, the quarks, and the gauge bosons. The leptons consist of the atomic electron and its two larger cousins, the muon and the tau, as well as three types of neutrino. The quark group consists of the up and down quarks, which make up the constituents of protons and neutrons, as well as their larger cousins, the charm, strange, top, and bottom quarks. The gauge bosons consist of the carrier particles for three of the fundamental forces of nature. These include the photon, the gluon, and the W and Z bosons. Finally, we come to the yet undiscovered Higgs boson. According to the standard model, all the elementary particles should be massless. The current best theory to explain how these particles attain their mass is called the Higgs mechanism. This is a simple demonstration of how the Higgs mechanism functions. It states that there is a scalar Higgs field which permeates all parts of the universe. Particles with no mass, such as the photon, do not interact with the Higgs field at all, maintaining their kinetic energy and passing through at the speed of light. A particle with mass, such as a quark, interacts with the Higgs field, which slows it down and converts some of its kinetic energy into what we know of as mass. In order to prove the presence of the Higgs field, the Higgs boson must be created and detected. This, however, has proven to be a difficult task, as the Higgs boson is predicted to be a massive particle, requiring huge amounts of energy to produce. The ATLAS detector is our tool for detecting the Higgs. It is situated at CERN in Geneva, Switzerland, and will be used to detect the high-energy collisions produced by the Large Hadron Collider. It measures 44 meters long, 25 meters in diameter, and weighs in at 7,000 tons. Two beams of protons will be accelerated in opposite directions close to the speed of light and collided at the center of ATLAS. How do you create a massive particle such as the Higgs from only two small protons? This comes down to Einstein's famous equation E equals mc squared, which tells us that mass is just another form of energy. By speeding up the protons, they acquire additional kinetic energy. The protons at the LHC are accelerated to 99.999999% the speed of light and acquire a total energy of 7 tera electron volts. This, combined with the energy of the other proton traveling in the other direction, produces a collision with the energy of 14 tera electron volts. Upon a collision, all this energy becomes hundreds of different kinds of particles. It is in these conditions which, if it exists, the Higgs boson will be created by the LHC and detected by ATLAS. Finding the Higgs will revolutionize our understanding of the origin of mass and help lead us to unraveling the other great mysteries of the universe.